especially I will concern with arsenic. You know, many countries of the world have this problem. And about 25 to 30 years back, Bangladesh, as a havoc caused by arsenic problem, we still remember, though the problem is less intensified nowadays in the surface level, but at the groundwater level, arsenic is still the problem because it comes from the upper stream, goes to the downstream, and there is a deposition in the sediment cell with arsenic. And you know that Dhaka, the capital city of Bangladesh, which is centered in middle of Bangladesh, and we are very much afraid, because I am living in Dhaka, and we are very much afraid that very near 10 to 20 kilometers away, like I don't know, the Narayanganj and Sonargaon, these two places have already been contaminated with arsenic. So what about this 20 kilometers is nothing? So suppose in one day, the water of Dhaka, which we are drinking now, it will have arsenic. So that is why we are very much concerned. So my aspect is not to determine the concentration of arsenic. It is the old problem. We are about the geophysical, geochemical and biochemical transformation of arsenic and the deposition of sediment and silt about the arsenic with especially other three elements like iron, manganese and copper, which are very much related with arsenic. So those three elements also very important for our study and their correlation also. Why is it not functioning? Oh, I see. And the backward. No, it's not. So, you know, the absorption, desorption reactions are very important. Determining the mobility of arsenic. In natural systems, attachment of arsenic to a metal oxide like iron, manganese, and copper also influence the variation of arsenic in groundwater, river bed, and cells. So, you know, the Bangladesh is a riverine country, and the three most important rivers, Padma, Meghna, and Jamuna, which originated from Malawi, and then passing through India, ultimately through Bangladesh, it goes to the Bay of Bengal. So, in Cairo 1940, people of Bangladesh uses river water not only for drinking but also for other purposes, especially for irrigation. Now, the background is that in 1993, that is already I have told you about 25 to 30 years back, it was a havoc caused by arsenic problem. So our total district is 64, out of that 61 has been affected with arsenic contamination. And a huge population is a health risk because arsenic, why arsenic is important? Because this affects our health and that is why arsenic is very much important to study. And to some extent, I have already told iron, manganese, copper, their presence also influences the concentration of arsenic. So that three elements is also important to study. And also some anions like sulfate or phosphate, which also related to some metal ions, especially with arsenic. So those also included in our study. Now, so this is the, the map, political map of arsenic. This pink color is mostly affected with arsenic. So, and other tone, these are white, but these are less affected, So one thing is important. When people, I have already told you, they use river water for drinking and other purposes. But when some waterborne diseases came into Bangladesh and many people died, and then UNICEF, they have launched a great project for Bangladesh to install deep wells throughout Bangladesh. in order to save some pathogenic and some organism, some bacteria which causes waterborne disease. But what happens after that? This water, deep well water, which is supposed to be free of any pathogenic organism that contains the great poison, that arsenic. So what we do then? So nothing is pure or safe for our health. So some health statistic arsenic has been studied. So community hospital in that time, 1903 arsenical patients have skin manifestations. The National Institute for Preventive and Social Medicine, they have listed 800 arsenicosis patients. The post-medical research, they have investigated 250 arsenical skin lesion patients. Besides this, patients with melanosis, leukomelanosis, keratosis, hyperkeratosis, dorsum, non-fading erythema, gangrene, and skin cancer have been identified due to arsenic contamination. So, but these figures are very old. So now, after that, it has been the figures have been multiplied much more. So now, with this view in mind, our objective is to study the mobilization from upstream to lower stream, their distribution in different zones, and their correlation, especially with the iron, manganese, and copper, as I told you earlier.
When you dissolve this in a more perturbing solvent, like acetonitrile, the dynamics are very much different now. The excited state seems to live for a very long time, and you see the appearance of this radical is there, as we saw in the gas phase, as we saw in the non-polar solvent. But you see also this tail here, and this tail is the triplet state. And this is characteristic of what people see with these phenols. Now what's happening is the OH bond dissociation channel seems to have slowed down, and other pathways are competing with this dissociation channel. And what this results in is a triplet state. And when you deuterate, by the way, what you see is that this radical feature disappears. And now we just have pretty much the triplet absorption. So what's going on? Well, one idea that we have, and this is where we need help from theoreticians, we really need help from theoreticians here, is that in the gas phase, in the gas phase and in a non-polar solvent, you preserve this intramolecular hydrogen bond here, okay? And in a polar solvent, what people have seen through Raman studies is that the intramolecular hydrogen bond is broken. And the electronic structure of this and this will inevitably be different, because this is actually buckled in the S1 state, whereas this guy is planar. Now, any small changes in the barrier height where this where this hydrogen is tunneling is going to dramatically affect this OH bond fission channel. Okay, so the take-home message is that in solution, while the weakly perturbing solvent is a good model, when it comes to a more perturbing solvent, then the dynamics start to change quite a lot. Okay, so let me just conclude by saying that we've observed tunneling-mediated dynamics in phenol. We can tune the tunneling behavior with substitution. Now, the gas phase does serve as a good starting point for the solution phase, but like I've just hinted, as you go to a more perturbing solvent, things start to drastically change, and we really need help here through modeling to actually really start to understand what's going on. Now, we saw that we can generate toxic free radicals, for example, the tertiary butyl catatoxyl radical. Now, this is dependent on what solvent you put the molecule in. Now, when you start to go to dihydroxyindole, which is what we're going to look at next, then do we switch off this channel completely? Do we not generate any radicals, for instance, and we just generate a triplet state? This would agree pretty much with what people have seen recently in a really nice science paper where where the eumelanin is quite an interesting molecule. A lot is to be learned in this molecule. There's a controversy whether it's photoprotective or phototoxic. And what this paper is telling us is that these long-lived triplet states are really bad for you, essentially. So can we bridge the gap, essentially, and really understand what's going on here, which will help us understand more what's going on here. So let me just finish off by saying that I've got to say a huge thanks to Team Stavros here. If it wasn't for these guys, I wouldn't be here. Some key collaborators responsible for some of the work that I've presented, my Cash Bowls group, and also some collaborators at Heriot and Berkeley, and some funding. And lastly, Gamsa Hamnida. I hope I said that right. Thank you. Now it's time that implicated the role of pi sigma start states, and they proposed that this could be due to tunneling, along with Christophe Jouvet's group. And we decided, well, because we can probe the appearance of these hydrogens in real time, let's just do exactly that experiment. Let's track the appearance of these hydrogens, and let's see if we can model this with some very simple tunneling calculations to see if there's good agreement. Now, the hydrogens that we saw appeared on a very long time scale, a nanosecond or beyond, and our simple tunneling calculation showed about 2.5 nanoseconds. Now, okay, so this is the experiment, this is at the origin, this is a slightly higher energy, and what you see is the rise in the hydrogen signal, up to 1.2 nanoseconds. That's the maximum delay in our experiment, by the way, time delay. You see it rises, and the solid lines are actually fits using this 2.5 nanosecond lifetime. So the agreement is pretty good. Okay, so this kind of agreed with this proposed mechanism by Mike and his group. Okay, so we then thought, well, what happens? Can we tune the behavior? Can we manipulate this through chemical substitution, this tunneling behavior? And a lot of work has been done. I'm just highlighting some key papers, most recently by Sankya Kim's group, beautiful, in JPC that appeared a few months ago on thiophenol. But we were specifically interested in catechol here. Now, the reason for catechol is because it's actually a moiety in dihydroxindole and dihydroxindole carboxylic acid. This is the building block of eumelanin, which is provides you the brown pigment in your skin that provides you with a frontline defense to UV radiation exposure. So we decided to study this and see if it shows similar dynamics to what phenol shows. So it's quite different. You see the appearance of hydrogens now, it plateaus almost at 40 picoseconds. And the time constant down is not nanoseconds, it's picoseconds. Now we can also probe the S1 decay. Now instead of detecting the hydrogens that come off as a function of pump probe delay, we photoionize from the S1 state in phenol. We look at the catechol cation as a function of pump probe time delay. And we see its decay. And this is essentially showing us as the S1 state is decaying, so is the catechol cation signal decay. And it agrees really nicely. So what this kind of tells you is that the S1 state, the dynamics is driven by this OH bond fission. Okay? Now the question is it tunneling or not? Well, we decided to deuterate this. And what you find is that the time constants dramatically increase. And this gives you a kinetic isotope effect of around 30. So that's pretty strong evidence that there's some tunneling going on in this molecule. So simply adding an extra OH changes the dynamics quite a lot. Now, I just want to, as a side note, we saw some wave packets earlier, beautiful wave packets. So what we did with catechol is that when we ionize from the S1 state, if we select a wavelength that's just above the IP of catechol, okay, then in addition to seeing an S1 decay, as we saw earlier, what we see are these oscillations superimposed on this decay, and you can fit a sine wave to this and then take the Fourier transform, and you get a frequency of 108.16 wave numbers. This is actually the torsional motion of the free OH. So some really, really fascinating things you can find out from doing the gas phase experiments. And this was really largely inspired by some of the work we did with Tim Swear's group on plant building blocks. So, okay, so can we transition this knowledge? That's the question, to the solution phase. So, okay, let's talk about the solution phase. The experiment involves excitation, yeah? But now, instead of probing the hydrogens that come off, we probe the radical itself, the catatoxyl radical, co-fragment, through a white light probe. So it's a transient absorption, essentially. So what we do is, here's the experiment, very simple experiment. We have our pump pulse, irradiates the sample that's flowing through a gravity jet or flow cell, okay? And then we have our white light probe that comes in and measures the absorption spectrum of the intermediate that we're interested in, for instance, or the excited state. So what do we see? Well, okay, in catechol we actually saw 0, nothing. And the reason for this is because catechol does not dissolve in non-polar solvents. That was a really, it was quite disappointing at the start. But then we thought, well, we're chemists, we have degrees in chemistry, so let's think about how we can modify this molecule. So we decided to choose tertiary butyl catechol, which means that this extra giant side group makes it more soluble in a non-polar environment. Remember, we want a weakly perturbing solvent first, and then a more strongly perturbing solvent. Now you might say, well, this might behave differently from catechol. Well, we tested this, we ran gas phase experiments, and it's pretty much the same as what we see in catechol, for tertiary butyl catechol. So we were okay with that. So now, let's see the data. So what you're seeing here is our white light probe is 350 to 650 nanometers. So what you see here at 1 picosecond, this is the absorption spectrum we measure. And over time it decays, it decreases, and by 2 nanoseconds you have this feature here. And this feature is already present at 1 picosecond. And this is the tertiary butyl catatoxyl radical. It's actually behaving as we see in the gas phase, okay? You excite the molecule, you get OH dissociation, you generate the tertiary butyl catatoxyl radical. So we were really happy with that result, actually. Now you deuterate this, and these are not very easy experiments to do. In the gas phase, we're spoiled. We have mass resolution. We can select, we can gate. In the solid solution phase, we don't have that. So it was very challenging. We had to run NMR spectra every time we ran these experiments to make sure our sample hadn't exchanged with water moisture in the atmosphere, for instance, or water in the solvent, in the cyclohexane solvent. And what this returns is a kinetic isotope effect of 4 versus what we were seeing earlier in the gas phase of 30. And what that's telling us is, well, we can't really say if it's tunneling or not, but we can say it's likely a barrier process to OH bond dissociation. So, okay, when you dissolve this in a more perturbing solvent like acetonitrile, the dynamics are very much different now. The excited state seems to live for a very long time, and you see the appearance of this radical is there, as we saw in the gas phase, as we saw in the non-polar solvent, but you see also this tail here. And this tail is the triplet state. And this is characteristic of what people see with these phenols. Now what's happening is the OH bond dissociation channel seems to have slowed down, and other pathways are competing with this dissociation channel. And what this results in is a triplet state. And when you deuterate, by the way, what you see is that this radical feature disappears. And now we just have pretty much the triplet absorption. So what's going on? Well, one idea that we have, and this is where we need help from theoreticians, we really need help from theoreticians here, is that in the gas phase, in the gas phase and in a non-polar solvent, you preserve this intramolecular hydrogen bond here, okay? And in a polar solvent, what people have seen through Raman studies is that the intramolecular hydrogen bond is broken. And the electronic structure of this and this will inevitably be different, because this is actually buckled in the S1 state, whereas this guy is planar. Now, any small changes in the barrier height where this where this hydrogen is tunneling is going to dramatically affect this OH bond fission channel. Okay, so the take-home message is that in solution, while the weakly perturbing solvent is a good model, when it comes to a more perturbing solvent, then the dynamics start to change quite a lot. Okay, so let me just conclude by saying that we've observed tunneling-mediated dynamics in phenol. We can tune the tunneling behavior with substitution. Now, the gas phase does serve as a good starting point for the solution phase, but like I've just hinted, as you go to a more perturbing solvent, things start to drastically change, and we really need help here through modeling to actually really start to understand what's going on. Now, we saw that we can generate toxic free radicals, for example, the tertiary butyl catatoxyl radical. Now, this is dependent on what solvent you put the molecule in. Now, when you start to go to dihydroxyindole, which is what we're going to look at next, then do we switch off this channel completely? Do we not generate any radicals, for instance, and we just generate a triplet state? This would agree pretty much with what people have seen recently in a really nice science paper where the eumelanin is quite an interesting molecule. A lot is to be learned in this molecule. There's a controversy whether it's photoprotective or phototoxic. And what this paper is telling us is that these long-lived triplet states are really bad for you, essentially. So can we bridge the gap, essentially, and really understand what's going on here, which will help us understand more what's going on here. So let me just finish off by saying that I've got to say a huge thanks to Team Stavros here. If it wasn't for these guys, I wouldn't be here. Some key collaborators responsible for some of the work that I presented, my Cash Bowls group, and also some collaborators at Heriot-Watt and Berkeley, and some funding. And lastly, Gamsa Hamnida. I hope I said that right. Thank you. Proteins absorbs light, but it's able to diffuse its energy in a non-destructive way. Okay, and we want to know what's going on, and that's triggered this research, certainly from my point of view. So our DNA absorbs radiation, but there is damage that does occur. For example, adjacent thymines combined to generate a dimer. Sorry, I've got it here. So you can get a dimer form, but then nature solved this as well. We have photolyase enzymes that are activated by light that come along and break this bond and generate the original DNA again. So everyone's happy. So from an energy level perspective, what's going on? Well, we have the ground state. This can be for example, a DNA base, adenine. It could be a chromophore of an amino acid. We excite this from the ground state to the excited state with UV radiation, and this state can fluoresce. Now, it could also undergo photoreaction. As I said, two adjacent thymines can form a dimer, and this outcompetes the fluorescence. But also, this excited state can return back down to the ground state, as you can see here, and it's mediated through intermediary states. And this, for example, this can convert harmful electronic energy into vibrational motion or heat. Okay? Now, intermediate states such as pi sigma star states can actually achieve this, and the importance of these pi sigma star states was noticed by Professors Domke and Sokolovsky, that said that they're very efficient for converting this harmful electronic energy back to the ground state into vibrational motion. Now, these are dissociative along a heteroatom hydride bond coordinate, XH. So X could be nitrogen or oxygen. Okay, so one might argue, well, if they're photoprotective, yeah, well, you're generating radicals here, so this can't be a good thing, right? Now, remember, in a DNA base, in a real system, you have base pairs, so you can get hydrogen transfer from one base to the other. And a lot of really beautiful work has been carried out in this area. Recently, Bernd Kohler's group and also Gareth Roberts in collaboration with Andrew Ewing's group at Bristol have tracked this in real time. This is amazing work. Now, I forgot to say that in my previous slide that the hydrogen atom loss from adenine, for example, a lot of this work has been carried out, beautiful work by Mike Ashfield's group, again at the University of Bristol. So, okay, so we use a bottom-up approach to understand processes, photochemical processes in larger molecules or more complex environments. Okay, so I'm going to be telling you a lot about phenol. I'm obsessed with phenol, by the way. Yeah, I love this molecule and different varieties of it. So we're going to zap it with a laser, okay, and then we're going to study its photochemistry in the gas phase, and then we're going to transition this to the solution phase. Put this in a non-polar solvent, a weakly perturbing solvent, and a strongly perturbing solvent such as methanol acetonitrile, and see what knowledge we can gain, or what knowledge we can apply from the gas phase to understand what happens in the solution. Okay, so our previous speaker did a great job about talking, telling us a bit about imaging. So I'm going to briefly skip over, briefly go into this, but just suffice to say we excite our molecule from the ground state, our phenol, to some excited state. This undergoes dissociation. We can probe these hydrogens that come off, by the way, in real time using 2+1 resonance enhanced multiphoton ionization. And what we have is a velocity map imaging setup where we have our pump pulse, excites the molecules, our probe pulse comes in at well-defined time delays, ionizes the hydrogens, and these are accelerated on to a detector, and then we reconstruct this 2D image to generate a kinetic energy spectrum. And the important thing to note about all these measurements is that these hydrogens that are dissociated through pi sigma star states carry off well-defined kinetic energies. That's why we can actually focus on particular areas in our kinetic energy spectrum to look at the dynamics of these hydrogens formed through pi sigma star mediated dissociation. And we studied a lot of these molecules, but phenol is the one I'm going to talk to you about. These are potential energy cuts along the OH bond. As you can see, this is the ground state of phenol, this is the excited state, first excited state, and this is the second excited state. This is the dissociative pi sigma star state. And as you can see, there are two conical intersections here. So excited state flux from one state
এই যে এখানে গরম পানিটা।
হ্যাঁ 1 ঘন্টা আগে নষ্ট
গরম পানি দিলেই হয়ে গেল। ওর মধ্যে দিতে হবে, খালি হয়ে গেল।
গরম পানি দিয়ে
হচ্ছে
সবাই হয়ে গেল।
দ্রুত
তোমার আবার ভিডিও হয়ে যাচ্ছে। হ্যাঁ, এত দাম যখন ভিডিও হবে না।
দুই পাশে নাম আছে। ওটা নিব না ভয় নাই।
চিলি পাউডার আছে
না নিবি না, এখন ওটা অন্য কথা। নাম দেখে কনফিউজ হয়ে গেছে, এইটা মধু এইটা মধু।
সমস্যা নাই, দেখছে তো আমার প্রফেসর। আর খেতে আর দেখলেই কি
জানার তো আমার
ঝাল হবে না, লাগলে সহজ।
তোমাদের ক্ষেত্রে সহজ, সহজ।
আমি তো স্যার
একটু ঢেকে রাখেন, একটু ঢেকে রাখেন।
কোনো কিছু রাখার থাকে না।
হ্যাঁ,
ওই হোটেলটাতে ওই হোটেলের ফিস তো জানি কত দেয়।
500 মধ্যে পান
পানি আনবো
এমনি পানি,
নর্মাল পানি।
বেশি দিও না।
কারি পাউডার
নর্মাল আবার বেশি। পানি কি কম হয়ে গেল নাকি? না, ঠিক আছে। হ্যাঁ, জানি না কীভাবে কত লাগে।
খুব বরফ তো এটা
আর তো পানি লাগবে।
1 মিনিট রাখলে সব